right, so this is to answer two questions that were emailed to me. Questions, let's see, 5.2, 23, and 25. I'm going to do them both in this this video here. So reading from the textbook, 5.2.23 has kind of a setup. So I'm going to read it and paraphrase it on the digital whiteboard here. A widely used method for estimating eigenvalues of a general matrix A is the QR algorithm. That's actually something we're going to learn in the future. Under suitable conditions, this algorithm produces a sequence of matrices all similar to A. Remember, to be similar to A, you have to have an invertible matrix P such that P inverse A, P, is equal to whatever you're saying it's similar to. So some similar matrix P. Anyway, it produces a sequence of matrices that become almost upper triangular. So these will almost become upper triangular with diagonal entries that approach the eigenvalues of A. Now remember, this is going to be a sequence of matrices. So the main idea is to factor A, or a matrix similar to A, into the form A times Q sub 1, or sorry, A equals Q sub 1, R sub 1. So essentially, you're going to factor A into the product of two matrices. Okay. And then, well, there's actually, they also state this, where Q transpose is equal to Q inverse. So I'm going to just say Q sub 1, I'm going to say Q sub I transpose is equal to Q sub I inverse, because this statement's can be true for all iterations. So no matter what, Q sub I, or Q sub whatever we're at, transpose will equal Q sub whatever we're at inverse. Okay. And then what we'll do is we will create a brand new matrix A, which we'll call A sub 1, which is going to be, well, not the inverse, but, you know, we're going to commute the multiplication of these two matrices. And remember, matrix multiplication is actually typically not commutable, but we're creating a brand new matrix A out of the commuted version of the QR factorization. And then we're going to go ahead, once you figure out what this is, you'll trade it out, not trade it out, but once you multiply R1 times Q1, you get your new matrix A and you refactor that. But you're going to refactor it into a Q sub 2, R sub 2. Okay? And then you'll build A sub 2 to be the commuted form of that. So R sub 2 times Q sub 2. You'll multiply those two matrices together. And then when you do, you'll refactor and you get Q sub 3, R sub 3, and so on and so forth. So this pattern continues not forever, but until you get an approximation of your eigenvalues as the diagonal elements. Anyhow, so let's see. I'm just reading. The similarity of A sub 1, and ... follows from the more general result in exercise 23, which is the one we're about to do. Show that if, so we want the if here. This starts, by the way, exercise 23. Show that if it's true that A is equal to QR. Now, here's what's the problem with question 23 is that the author, if he's trying to stick with what he wrote down in the previous paragraph that we wrote down here, he probably should have written, well, if A is equal to Q1, R1. But that's okay. We're just going to assume that's what this here is. So I'm just going to do that. If A is equal to QR, we want to, with Q invertible, where Q inverse exists. Okay. Show that that implies that A is similar. Then A is similar to A1, which is equal to RQ. Now, if A is equal to QR, here comes my work. I'm going to write my work in yellow. If A is equal to QR, well, that implies, since Q is invertible, that implies Q inverse A is equal to R. I hope that makes sense. And if I multiply both right-hand sides by Q, then I get the following. Q inverse A Q is equal to R Q, which we're defining to be A sub 1. Therefore, A is similar to A sub 1. There actually was not much in this, right? It just, you actually didn't even use this entire derivation right here, to be honest with you. So not much to it. The language leading up to it is kind of weird, but it actually is a truth. We just haven't reached that materially yet. That's in chapter 6. But anyhow, that's all that was required in this problem. All right. And then 25. 25 is an interesting one. And I'm not looking at your assignment online, so I can't remember if you did. I guess it's example 5 from 4.9. Anyway, we're going to let A be the matrix given by, let's see, 0.6, 0.4. And you know what? I'm going to write this as 6/10 because I'm going to do all my math by hand. And so it's just easier for me to do it this way. 6/10, 4/10, 3/10, and 7/10. Okay. It's just a little bit cleaner, I think, for me personally. And then V sub 1 is a vector. Very special vector they're going to tell us about in a moment. And that's 3/7 and what is it? 4/7. Another reason why I wanted to get rid of those decimals, because they're mixing decimals and fractions. And then X naught is the vector 1/2, 1/2. All right. So that's the setup. And then they give us a big fat hint. Note, A is the stochastic matrix studied in example 5. Actually, I'm not even going to bother looking at example 5 in section 4.9. The reason why I know this is a stochastic matrix, or in other words, it could be a Leontief model or a Markov chain, is that if you look at the columns, they sum to 1. In other words, the first column, 6/10 plus 4/10, is going to be 1. In the second column, 3/10 plus 7/10 is going to be 1. That's a very, 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 very special matrix. Incredibly important. And so important that I did an example of one of these at the end of one of the videos. I can't remember which one at this moment. It doesn't really matter, but I'll remind you of it here. So part A, find a basis for R squared consisting of V1. So we want our basis to consist of V1. Since it's a basis for R squared, we need 2 vectors, right? So I'm going to say NV2, but we don't know what V2 is yet. But they give you a big fat hint here. Find a basis for R squared consisting of V1 and another eigenvector, V2 of A. So they're already telling us V1 is an eigenvector of A. So I'm going to go ahead and find the corresponding eigenvalue. That's just going to help out. You don't actually have to start by doing this, but you're going to have to do this eventually. So since they kind of hinted that V1 is an eigenvector, I'm going to go ahead and figure out what the corresponding eigenvalue is. So if I take A times V1, I'm not going to have to write those there. I could just see the mathematics here. It'll be, which is exactly, V1. I'm trying to erase that. Didn't quite work out. So notice that our eigenvalue corresponding to the eigenvector V1 is 1. The reason why I wanted to do that is because you want to find the other eigenvalue, and you'll see that knowing one of the eigenvalues makes the factorization kind of simple, or easier, I should say. So to find the other eigenvalue so we can find the corresponding eigenvector, I will go ahead and solve the characteristic equation 6/10 minus lambda. What is it? 3/10, 4/10, and 7/10 minus lambda is equal to 0. So again, that's just the characteristic equation. Now, the reason why I wanted to find the eigenvalue earlier for vector v sub 1 is that eigenvalue of 1, that's going to be one of the two roots of this characteristic equation. So I happen to know when this factors, it's going to be, well, let's see, I have my choice to factor this to 2 and 5 or to factor it to 10 and 1. And I happen to know it's probably going to be the 10 and 1 because I need one of my roots to be 1. So I know the other one's going to be 10 lambda and let's see, minus 3. Now you can double check, right? So that'd be a 10 lambda squared minus 3 lambda minus 10 lambda, which is negative 13 lambda plus 3. Yep, perfect. So my other eigenvalue is 3/10. That's lambda sub 2, let's just call it. Okay, lambda sub 2 being 3/10, you can find out the corresponding eigenvector. So I'll let x sub 2 equal 1 to find a, or I should say to find an eigenvector associated with the eigenvalue 3/10. So I happen to know another eigenvector that for our basis is going to be negative 1, 1. So let me go ahead and write our basis in here. Our basis is going to be, what do we have? You actually don't have to have the 3/7, 4/7. You could write as 3, 4. Remember, a scalar multiple of an eigenvector is still an eigenvector. So I'll just write as 3, 4 and negative 1, 1. They might want us, and actually it might be beneficial, I'm guessing, to leave it as 3/7, 4/7. But for right now, I'm just going to call it 3, 4. All right. So that was a lot of work for part A, right? Well, part B, verify that x sub 0 can be written in the form x sub 0 equals v1 plus c v2. All right, let me write part B down here first of all. B, can x not be written as v1, the v1 they handed me, not the v1 that that I modified for our basis, but 3/7, 4/7. Okay, plus some constant times, sorry, I'm losing my place on this page, v2. Okay. So remember x naught, the vector, was 1/2, 1/2. v1 was 3/7, 4/7. Is that what it was? Yeah, that's what it was. Plus c times, and then we found v2 to be, was it negative 1, 1? Yeah, negative 1, 1. Negative 1 there. Now, you can actually just move things to one side. So c should be negative 1/14. All right. So we have shown that x naught can be written as a linear combination of those two eigenvectors. That's actually the punchline here, that x naught can be written as a linear combo of the eigenvectors, and that is how you really want to write most of your vectors if you can, because when you start taking powers, remember, I had this in a video, that if you start taking powers of a matrix times an eigenvector, so let's say a to the 50th times an eigenvector v sub 1 will actually be the eigenvalue to the 50th times the eigenvector v sub 1. That's going to be very, very important actually for this problem. So part C says the following: for k equals 1, 2, and so on and so forth, define x sub k, the kth iteration of x, to be, I'm trying to find it, a to the k power times x sub 0, which is exactly what I had just mentioned here, that a to the kth power, if x sub 0 is an eigenvector, or even if x sub 0 is a linear combination of eigenvectors, so plus c, which we've just proven is negative 1/14, v sub 2. You could distribute that a sub k through, or a to the k, sorry, v1, minus 1/14, a to the kth power v sub 2. This is this is really a very, very important style of problem. And then if you, let's see, compute x1 and x2, I'll let you compute that. That's not that big of a deal. Remember, this, because these are eigenvectors, that's going to be lambda sub 1 to the kth power times v sub 1 minus 1/14 lambda sub 2 to the kth power v sub 2. And remember, our lambdas are, what are they? Lambda sub 1, remember, was 1. And lambda sub 2 was the ugly one, as I recall, 3/10. There we go. So let's go ahead and write that in here. This is going to be 1 to the kth power times v sub 1 minus 1/14 times 3/10 to the kth power v sub 2. And the important piece about this to think about is, if your eigenvalue is less than 1 in magnitude, then for high powers of k, that will tend to 0. If your eigenvalue is 1, then it doesn't matter what your high power of k is. It's 1 to the kth power, which is 1. And so in the long run, the pattern or behavior of x sub k is going to mimic the eigenvector v sub 1. So it's saying then show that x sub k approaches v sub 1 as k goes to infinity, basically. And it is true. As k goes to infinity, x sub k will tend to, well, that tends to 0, so v sub 1. There you go. So that is both 23 and 25. Of those two, 23 is a little bit wordy. I would not have something that crazy worded on an exam. Definitely not. However, similarity definitely will be on the exam. And then 25, I really like these iteration style problems. So I might give you a matrix where the columns add to 1. It might be nice to show that you know that little subtlety. It is a very, very powerful theorem if you can use it, or a very powerful application of powers of matrices and their associated eigenvectors, eigenvalues. So it's very, 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 very important for certain industries. Anyhow, that's it. All right. I hope you have a good day.